So now we were talking about intermolecular forces, and when we were talking about intermolecular forces, this is what we did. Okay, you've got bonds, and those bonds, if there is an electronegativity difference between elements in a bond, then the electrons are going to be closer to one of the atoms, and that would result in a dipole. And if there is no electronegativity difference, then the molecule would be nonpolar. And sometimes the electronegativity difference is huge. In that case, you get an ionic bond. The electrons completely are gained by one of the atoms. So if there's an atom over here and there's an atom on the extreme left and they're bonding together, then that's probably going to be ionic. So if the difference is less, it's going to be polar. If there is no difference, it's going to be covalent. And I told you about the shape of the molecule, that it depends on the shape as well. So you need to connect this with the shape of the molecule. That sometimes what would happen is that the molecule would be completely symmetric, planar. So all the electrons, all the forces of attraction are going to get cancelled out. Like in this case, the electrons are getting pulled in different directions. So the electrons are going to stay wherever they are because the force of attraction are going to get cancelled out. And sometimes all the electrons are going to get pulled downwards, depending on the shape of the molecule. So sometimes they're going to cancel out, sometimes they're not going to get cancelled out. And then we talked about the strength of dipoles, that sometimes the difference is very large. So for example, if you look at this molecule, there's a Cl atom over here, which is very electronegative. The H atoms are not very electronegative. So the Cl would try and pull the electrons to one side. So this side would be partial negative, while the rest of the H atoms would have a slight positive charge. So that was dipoles, permanent dipoles. What we're going to study next is called the second type of attractive force, and that's your hydrogen bonds. Okay, those are your hydrogen bonds. And so what happens in hydrogen bonds? What happens is that it's an extreme, in simple words, it's an extreme version of a dipole. So hydrogen bonds, they occur in those molecules. So it's the same concept as a dipole. We had the electronegativity table. Now, the most electronegative elements that you have are these ones over here, the ones that I'm going to shade. Okay, let's I mean it's these ones over here. Just 1 second. So the most electronegative elements are the ones right in the corner. That's nitrogen, oxygen, and fluorine. These are the most electronegative elements. So in that case, so it's an extreme version of a dipole. So there are a couple of conditions. First one, the molecule must have it must have the most electronegative elements in the periodic table, the ones that really like to attract electrons. And there are 3 of them. That's nitrogen, oxygen, and fluorine. And they must be bonded to hydrogen directly. So they must be bonded to each directly. And the second condition is that there must be lone pairs. Lone pairs should be available on these atoms, nitrogen, oxygen, or fluorine. So it's just an extreme version of a dipole. This is what's going to happen. For example, if I have an HF molecule. Now, the HF molecule has one of the most electronegative element in the entire periodic table. It's got that. So there's going to be a very, very strong attraction for electrons towards one side. Like the bonded pairs of electrons, the bonds that is being formed over here, the electrons are going to get pulled towards one side, and they're going to be pulled towards one side very strongly. It's almost going to be an ionic compound. Like the fluorine would almost, like it would so strongly attract the electrons that the electrons are almost gained by fluorine, but there's some kind of sharing going on. So the electrons are not completely gained by fluorine in this case, because the electronegativity difference is not that huge. Like if I refer to the electronegativity diagram again, like the electronegativity difference is huge, but not that huge. This is 4. Fluorine over here in the corner is 4. This one is 2.1. I mean, ignore the value. I mean, the difference is there, but it's not that large. It's not like the difference between fluorine and sodium. Sodium is like 0.9. I mean, look at francium, that's 0.7. So fluorine and these elements, the difference is huge. In that case, you get an ionic compound. But when fluorine is bonded to H, the electronegativity difference is there. It is large, but not very, very large. So it's very large compared to covalent molecules. So the molecule remains covalent. The electron sharing continues, except that the electrons are very strongly attracted to one of the atoms. So that side is going to be, it's going to have a very strong partial negative charge, and the other side would have a very strong partial positive charge. TK, is this point clear? Mariam, is this clear? Anna?
Yes, sir.
TK, so there's going to be a very strong partial negative and partial positive charge because fluorine is so electronegative. The other part is, if there's another HF molecule, so it's exactly like a dipole. So the other HF molecule, the same situation would happen. There's going to be a very strong slight negative charge, and the other side would have a very, very strong slight positive charge. So there's going to be a lot of attraction between them. There's going to be very strong. This is known as a hydrogen bond. I mean, that's the first thing. There's a huge electronegativity difference. So very strong dipoles are created. But the force of attraction is not only strong because of that fact, but there's another fact. The other fact is that these 3 atoms have lone pairs. What that means is that when you look at a fluorine atom, it's got lots of spare electrons. Like there's 6 of them. There are going to be 6 spare electrons. This fluorine atom would also have 6 lone pairs, 3 lone pairs basically. I mean, the outer shell of fluorine has a lot of electrons. So the negative charge is also large. It's also greater because of these spare electrons. Like if this H positive is attracted to this fluorine, fluorine has a lot of spare electrons, and those electrons will increase the negative charge. So there's another reason for the negative charge being really strong. So lone pairs on F, which is a small atom. It's a tiny atom. Like fluorine has just 9 electrons. So it's a pretty tiny atom. I mean, all 3 of them are really tiny atoms. That's nitrogen, oxygen, and fluorine. So lone pairs on F, the unused electrons that are not involved in bonding in the outer shell, you've got lots of them. So lone pairs on F have high charge density. What that means is that the electrons, because it's a tiny atom, the electrons are really concentrated. They're occupying a very small area because it's a small atom. So the negative charge is also stronger because of that. I mean, the negative charge is not spread out over a bigger area. TK, the negative charge is all very concentrated over a very small atom. So they have a very high charge density, which is why the attraction is even stronger. TK, is this point clear? TK, Alicia,
Yes.
is this clear? So the attraction is even stronger. So there are 2 factors, TK. One is that it has a very strong dipole. TK, the electron in the bond are very strongly attracted to fluorine because fluorine or oxygen or nitrogen, they're very electronegative. So the negative charge, the positive charge are really strong. But the other factor is that there are lots of spare electrons, and it's a small atom, so the electrons are very concentrated. That also increases the negative charge by a lot, by a very large amount. So the negative charge is very strong. So the force of attraction is pretty strong because of these two facts. I'm going to highlight those two facts. One of them is about it's about the lone pairs, and the other one is you've got the most electronegative elements that are involved. So this is not just a very it's a pretty strong attractive force. So hydrogen bonds are relatively the strongest. So they are relatively one of the strongest intermolecular forces. So relatively one of the strongest intermolecular force. And so we're going to talk about the other ones as well. You've got water molecules like oxygen bonded directly to H. So that is also going to have hydrogen bonds. The shape of an oxygen molecule is tetrahedral because it's got so the shape of an oxygen molecule is tetrahedral. I mean, it's going to be bent because on the other side, there are just lone pairs. Oxygen has two lone pairs. So these are your spare electrons that are not involved in bonding. Like these are completely full orbitals, which are initially not involved in bonding. So the OH bond is going to be very, it's going to be very polar because oxygen is extremely electronegative. So oxygen would try to pull the electrons in the bond, and oxygen would try to pull the electrons in this bond. So the H will have a very strong partial positive charge, and the lone pairs over here will have a very strong partial negative charge because of two reasons. Firstly, there are spare electrons, so electrons are negatively charged. The other reason is that the oxygen atom is also pulling electrons away from hydrogen, so the negative charge on these lone pairs would be pretty strong. So if there's another water molecule, just a second. So there's other water molecules. So I mean, you'll be asked to draw these hydrogen bonds. What you just have to do is just sketch a dotted line, which would show that there is an attractive force between water molecules. The positive H of one water molecule would be attracted to the negative lone pairs of the other water molecule. So that's your hydrogen bonding going on. Okay, is this point clear? Yes, sir. Zahib, is this clear? Alicia, Anna, Mariam?
Yes, sir.
Yes, sir.
So now the last one is we can also talk about N bonded directly to H. Now N makes 4 bonds. It's also derived from a tetrahedral shape, except that the top is missing because there's no bond there. Instead, you have a full orbital. So the shape is trigonal pyramidal. It's like a pyramid. Now N over here is also extremely electronegative. So plus it's got this lone pair as well. The H atoms over here would have a pretty strong positive charge. The N atom being extremely electronegative would be pulling on all the electrons towards itself, and this top would be extremely negative. And it's going to be even more negative because of the pair of electrons that's just there. Okay, so that would add to the negative charge. So again, it's a highly polar molecule, and because of the extra lone pairs, the attraction is even greater. So if they are two ammonia molecules, then if they ask you to draw this, all you have to do is that the H atom will be attracted to the lone pairs on N on the other molecule. So that's your hydrogen bond that is being formed. So now similarly, you will have a so can anyone tell me who out of these three, who is going to form the maximum number of hydrogen bonds? Like, would it be HF? Would it be water? Would it be ammonia? क्या होगा? Anyone any idea?
HF.
ठीक है. अच्छा, now I mean, HF would probably be the most polar because fluorine is the most electronegative. Like if you go over here, so fluorine is right at the top, right? So fluorine would probably be the most polar. But the thing is that the quantity of hydrogen bonds that would be formed would actually be lesser. And the reason for that is, like, imagine you've got lots of HF molecules, right? Now the HF molecule, if you analyze the HF molecule, it's got 3 lone pairs. But it's got only one H atom that has a partial positive charge. I mean, it's got 3 lone pairs. All 3 of them would have a very strong partial negative charge, right? But there's only one H positive. So that means if you have lots of HF molecules, you are actually short of, like, every lone pair will be attracted to an H positive. Like if you have a lone pair, that lone pair will be attracted to the H that is positive over here. So 2 of the lone pairs are getting wasted. I mean, you wouldn't be able to use them. So you've got too many lone pairs and too few hydrogens that are positive. Is this point clear? Yes or no? Okay. Water is the one that's going to be efficiently forming hydrogen bonds because it's got 2 lone pairs. Like every water molecule has these 2 lone pairs. So every water molecule has 2 lone pairs and it's got 2 hydrogens that are positive as well. So that means there's nothing getting wasted. Every time there's a lone pair, an H, I mean, you will have equal number of H positive. Like if you have thousands of molecules, the number of H that are positive, like in this case, like if you look at the picture, there are 4 H positive in the diagram and there are 4 lone pairs as well. So if you have thousands of them, no one would be getting wasted. Every lone pair will be attracted to an H positive. So it will be forming hydrogen bonds very efficiently. Okay, the quantity, nothing would be getting wasted. And the same is the problem with ammonia. I mean, ammonia has the same problem as HF. It's got just 1 lone pair, but it's got 3 H that are positive. So again, and there's only 1 lone pair. So the problem is that because of the fewer lone pairs, most of the H positive will get wasted. I mean, like if this H positive bonds with this lone pair, what will the other H positive bond to? They have nothing. They don't have any. You're basically running out of lone pairs. There are no lone pairs left, so that the other H positive would just get wasted. They won't be able to attract any lone pairs. Is this point clear?
Yes, sir.
Okay. So also remember that out of the 3, even though the hydrogen bonding is not the strongest in this case, but it's going to make the maximum number of hydrogen bonds because of equal number of lone pairs and positive H atoms. So more efficient hydrogen bonds are formed due to equal number of positive H atoms and lone pairs. That's just a second. So is this thing clear? Anya, is this clear? Zainab, is this clear?
Yes, sir.
अच्छा, इसके बाद moving on to other things related to this, and remember this one, water has the highest boiling point. Like it's got a boiling point of 100. Ammonia has a much lesser boiling point. HF also has kind of a lesser boiling point. Like I can show you the boiling point. Even though HF has a stronger hydrogen bond, but its boiling point is lesser because of the lesser efficiency. It's just 19.5. So that means the attractive forces are strong, but they're not that many hydrogen bonds to begin with. Most of the lone pairs are getting wasted. So now some properties about hydrogen bonding. So I told you that molecules that form hydrogen bonds their melting points and boiling points specifically are drastically higher compared to similar molecules. So they're drastically higher compared to similar molecules. So for example, if I show you the melting and boiling points of hydrogen halides, let's look at boiling points for a second. And if you can have a graph, and I'll just copy this one. So you can see that, I mean, this is water and HF. Water and HF had hydrogen bonds. So molecules that had similar, that were very similar to them, like HCl and HBr and HI, their melting and boiling points are kind of very low. And HF all of a sudden has a much higher melting and boiling point, simply because of hydrogen bonding. So over here, you've got hydrogen bonding going on in these two molecules, which is why the melting and boiling points are kind of really, really high. I mean, water has kind of, even though it's a covalent molecule, but it's got a relatively pretty high boiling point. Now, the other thing about there's some properties related to hydrogen bonding. So one of the properties is that that water expands when it freezes. When it freezes. So why does it expand? And this is due to hydrogen bonds. Now the expansion is pretty strong. It's a very strong expansion because pipes can break, steel pipes can break, explode. So the expansion is really, really strong. So why does this happen? When you've got when water freezes. So you've got these two water molecules. Okay, so I'm gonna take a couple of water molecules. Just a second. So I'm just going to take this water molecule, and I'm going to show you why it expands when it freezes. So here's one water molecule, and let's have a few more. So I've got these 3-4 water molecules. I'll have another one, and let's just rotate it. So when water is liquid water is energetic. Energetic, and that means that they're capable of overcoming or breaking those hydrogen bonds. So they easily overcome the attractive force. Overcome or break hydrogen bonds when they're in liquid state. For example, this H positive, I mean, you have this H positive that's bonded to, that's very strongly attracted to this lone pair, but the water molecule is energetic. So the water molecules will be slipping and sliding on their own. So, I mean, this water molecule would just move on, slip and slide. So it will not be that strongly attracted to this H positive. So the molecules would be arranged haphazardly because they're energetic. Okay, that's important. And whenever you have energetic molecules, the molecules can break the hydrogen bonds or attractive forces. Now, when they start to freeze, they start losing energy. So when they freeze, the same molecules, they all of a sudden they start to lose all the energy. I mean, you're taking away energy. That's what you do when you're freezing them. Now the molecules are not energetic enough to actually break the hydrogen bonds. So what happens is, now the issue would be that if you've got a water molecule, then a crystalline structure would start forming because the other water molecule will not be able to escape because it's not energetic enough. So the other water molecule will, its positive part and its negative part, they all stick together. Because this molecule has now lost energy, so it can't break this attractive force. It isn't energetic enough. If there's another water molecule, that water molecule would also arrange itself in a specific order. I mean, the positive and negative parts would attract, and it's not going to be able to move freely. Okay, so the water is freezing up. This molecule cannot move around. Is this point clear? And is this clear, Alicia, Mayim?
Yes, sir.
And so if there's another water molecule, the other water molecule would also do kind of the same thing. So it's I mean, that water molecule would align itself in a crystalline lattice. The positive and negative parts would attract. It will not be able to break that attractive force because it's not energetic enough. So what's happening is a very specific crystalline arrangement is forming, which is why gaps are being created. Because remember, water had a very specific bond angle, like the H atoms, they had an angle of 104.5. So if the H is over here, the positive H, the lone pair will be sticking on that side. I mean, this H over here is positive. So the lone pair of the other water molecule would be sticking over here. So that would result in the formation of a gap. There's not going to be anything in this gap over here. So all of a sudden, you're getting gaps. Previously, you didn't have any gaps because the water molecules could have easily broken the attractive forces. Like if this water molecule wanted to, because it's energetic, it's moving around. So if it wanted to come over here, even though the hydrogen bonds would be trying to pull it in other directions, but the water molecule was energetic. So it would randomly slip and slide wherever it wanted to go. It could easily break the hydrogen bonds. But now they're not able to break the hydrogen bonds. The attractive forces are too strong for them, and they have very little energy now because you're freezing them, that they can't just move around. They've lost their kinetic energy. So that's why gaps are created, and that's why water expands when it freezes. And the expansion is pretty strong. That's because of the crystalline arrangement due to hydrogen bonds. So is this clear, Zahib? Hania, is this clear, Mayim?
Yes, sir.
Anna, is this clear?
Yes, sir.
So remember this about hydrogen bonds, and hydrogen bonds are pretty strong. Together, one of the strongest attractive forces between molecules. So water expands when it freezes. So the condition is that whenever you have N, O, or F directly bonded to H, and the other condition is that the lone pairs, they must be available. So it's not just these three molecules. It could be in other molecules as well. For example, if you've got ethanol So ethanol is CH3, like methanol. Let's talk about methanol. So methanol is CH3 and OH. I mean, O over here will have two lone pairs. The H will have a very strong positive charge because the O is directly bonded to H. That was one of the conditions. And the other condition was that the lone pairs on oxygen must be available. So that means it's got a very strong partial negative charge. So if there's another ethanol molecule, methanol molecule, or let's say there's another water molecule, so this H would be very strongly positive and they would be very strongly attracted to each other. So hydrogen bonds will happen in any molecule where O is directly bonded to H and where lone pairs on O are available. For example, if I take another molecule like an aldehyde, this one is serial bond O, NH. Can anyone tell me, will this form hydrogen bonds? Does it meet the conditions? क्या होगा इसका?
No.
ठीक है, so this one is not meeting the conditions because the O is not directly bonded to H, but it's meeting the other condition that the lone pairs on oxygen are available. So one of the conditions is met, the other one is not met. So that means it's got the negative part because of the presence of lone pairs. The lone pairs are going to have a very strong negative charge, but the O is not directly bonded to H. So the H is not going to be, so there's one thing missing. It's got the negative part, just not the positive part. So if there are two of these molecules, they can't form hydrogen bonds because you need a positive thing. It will be capable of forming hydrogen bonds with water because it's got the H positive. So remember, for hydrogen bonds to happen, either one of the molecule has the negative part and the other molecule has the positive part. I mean, this molecule on its own will not be able to form hydrogen bonds. Like it can form hydrogen bonds with water, but not with itself. Because with itself, there would be no H positive. So you would have to draw these hydrogen bonds using these dotted lines. So now we're going to study the last one. That's hydrogen bonding. Okay, we're going to do past paper questions later on this. The last one, the final attractive force, that is van der Waals forces. Okay, remember the first two that we studied, permanent dipoles and hydrogen bonding, they were kind of similar. Hydrogen bonding was just an extreme version of a permanent dipole. The last one is van der Waals forces, which are also known as temporary dipole induced dipoles or temporary dipole instantaneous dipoles. Let's call it instantaneous. Also known as dispersion forces. So this one is one of the weakest. Okay, relatively one of the weakest. So between molecules, it's going to be one of the weakest intermolecular forces. But the thing with this is that it increases with size. So you have to be careful about size. And if size is large, it could actually become really, really strong. Even stronger than hydrogen bonds. So this one depends a lot on the size. The other ones, they didn't really depend on size, but this one actually depends a lot on size. If you have the same size molecules, then this one would be the weakest out of the three. But if the size is really large, then it's probably going to be the strongest out of the three. Now, the thing with van Waals forces is they're also always present. Like all the molecules we studied, van Waals forces will be present. So what are van Waals forces and what is temporary dipole, instantaneous dipole? For example, I have a molecule of chlorine and I have another molecule of chlorine, and there are three molecules of chlorine. Okay, let's have this molecule, all three molecules in a line. As a first thing, can anyone tell me, is this polar or non-polar? Like, are the electrons towards one side or are they evenly distributed?
Evenly distributed.
Okay, so in this case, they are evenly distributed because both Cl atoms, they like to gain electrons. So, I mean, they're both pulling on the electrons and they're pulling on the electrons with equal force. So that means the electrons would stay in the middle. Okay, they're not going to go towards one atom or the other atom. So it's going to be a completely non-polar. There's no partial positive, partial negative charges. So why do they attract each other? I mean, it's completely non-polar. No positive negative charge, no positive negative charge on this, no positive negative charge on this. So theoretically speaking, these molecules should not attract each other at all. This molecule should not attract this one. This should not attract this one. So what happens is that the electrons, even though if the molecule is non-polar, all these molecules are constantly bumping into each other. For example, this molecule over here, it might go and bump with this molecule. It might go and bump or collide with this molecule. So molecules are constantly bumping around and colliding. When they collide, the electrons might get knocked to one side, and that would result in the formation of temporary dipole. I mean, during those collisions, randomly due to some random collision, the electrons might get knocked to one side, and that side would become slightly negative for a very temporary instance. And maybe right after 2 seconds, the molecule would bump or collide with another molecule, and the electrons might get knocked to the other side. So this side would become slight negative and this side would become slight positive. So what's happening is there's a temporary dipole that's always forming due to the collisions. Like if it was an isolated molecule, then it won't form a dipole. But molecules usually are not isolated. They're always bumping into each other. So the electrons are kind of getting pushed to one side or the other side during those collisions, and that results in the formation of a temporary dipole. Is this clear? Is this clear, Zainab?
Yes, sir.
Mariam?
Yes, sir.
Now, what's going to happen is that the electrons are constantly bumping into, they're constantly moving around. They're not due to collisions. So that is temporary dipole. What's instantaneous dipole or induced? It's also sometimes referred to as induced dipoles. What happens is that if this one gets a dipole for a very small, a few seconds, few microseconds, it's going to affect the other molecule. It's going to affect its electrons. Because if that other molecule comes close to it and tries to collide with it, the positive chlorine over here will try and attract the electrons from the other molecule. So this side would become slightly negative and this side would become slightly positive. So you're going to get a temporary dipole. And because of that temporary dipole, a dipole would be induced on the neighboring molecule as well. And if you bring the other one as well, let's say this Cl is now coming close to it and it's going to bump with it. The positive side over here will try and pull the electrons or will have a slight effect, and this side would become slight negative. This side would become slight positive. So But this is all changing. Like this next second, this dipole would change. It would switch, and all the other dipoles would also switch. But every second, there would be a dipole on all these molecules, and there would be some attractive force because there is now positive and negative charges. Even though they are fluctuating, they're not stationary, they're not permanent, they're all temporary, and the induced dipoles are also temporary. So, but there's this fluctuation that's going on rapidly and very, very constantly throughout the molecules, all the molecules. Like you'll have billions of them, and the electrons would be just sometimes they're on the left side, sometimes they're on the right side. Is this point clear? Abdullah, is this
Yes,
clear?
sir.
Chalo, theek hai.
Yes, sir.
Acha, let's continue tomorrow then with the same thing. Okay, we'll probably be done with this. Tomorrow we'll do past paper questions on this. Intermolecular forces. Okay. Okay, then take care. Allah Hafiz.
Allah
Allah
Hafiz.
Hafiz.
Allah Hafiz.